Okay, so how is everyone today? Good? All right. So we just turned in that homework there. And so there's two on that. Well, let me first write the date, I guess. So today's the 11th. So on that homework we just turned in, there's it's basically two different ways to calculate Euclidean division. That is to say, to calculate the quotient and the remainder. And that first one, the f function, is new in the sense that it has some new feature that we've never used before in our class. And as a result, many of you, I suspect, probably had a lot of difficulty figuring out how to write something intelligible, neat and organized about how to use f, how to show the computation. But I suspect that you found g and g tilde pretty straightforward because it's actually quite similar to, for example, the Fibonacci one, the Fibonacci pair that of auxiliary functions. All right. So the confession is that I did that on purpose. I purposefully, more or less, didn't show you a neat way to organize the computation for f, because historically what's happened is that I showed students in advance how to do it, and no one listened. And then then I asked for the homework, and because no one was listening, the homework is a disaster. Okay, and I suspect these are basically just the f part is probably just as much of a disaster as before. But now that I have your attention, that there's something that you need to pay attention to, I'm going to show you how to evaluate that f function in a nice and organized way. And if you don't get much credit for that part, then you'll be able to submit a redo. Thank you. All right. So then let's do it. So first I'm going to do the g function. So for example, divide 23 by 4. And I'm going to do it using the g one. I'm going to do the g one first because it's easy. So g of n and d, which is to say that one divided by that one, is defined as, I'm just copying the definition from the homework, g of n and d and 0. Okay, and then g tilde with inputs r and d and q is defined as, well, let's see if I can reason it out. So r represents how much remains, and d represents the group size. So if it ever comes to pass that what remains is less than the group size, that means that it's not possible to make any further groups. So that would mean that's the stopping condition. And in that case, the remainder should be r, and the quotient should be whatever that is. Okay, so then the answer would be r and q. Is that what I wrote on the paper? Yeah. I just wanted to make sure I have them in the same order as the order on the paper. Otherwise, which is to say that the number of items that are left, you have the number of items that are left is big enough to make at least one more group. So in this case, the answer would be g tilde of, well, what remains, and then take away d, because that's the effect of making a group. This is going to be constant because we're making groups of size d. And then that's the effect of making one group, so we need to record that we made one group, so q plus 1. Okay, so using that. So therefore the computation is something like g of 23 and 4. So the first thing that this g will do is it'll call g tilde of 23, 4, and 0. And effectively what that means is, the reason why that's the first step is because that's the third argument. That's Q. And that represents how many groups have you made so far? Well, none, right? We haven't made any yet. So can we make a group? Yeah. So you could imagine that this is something like, let's break, we have a group of 23 M&Ms and we want to make groups of size 4. We've got a pile with 23 groups of size 4. Can we make at least one group? Yes. So then that means the next evaluation would be G of 19 because we made a group, 4 because it's going to be 4 all the time, and then 1 because we made a group. And then it just continues, right? So this would be G tilde of 15, 4, and 2. And then the next one will be 11, 4, and 3. The next one, 7, 4, and 4. The next one, 3, 4, and 5. And now finally, something's going to be different. Because what this is saying is effectively that, well, there were 23 M&Ms, and then 19, and then 15, 11, 7, and then 3. And now that there's 3, now the behavior changes. How does it change? Yeah, now we're going to finally use this first clause. Because if we have 3 M&Ms and we're making groups of size 4, there's not enough to make another group. So we're actually finished now. So the output would be 3, 5. So we could say, therefore, the remainder is 3, the quotient is 5, and the Euclidean division is saying that 23 can be represented as 4 multiply 5 add 3. So the dividend is the divisor multiplied by the quotient plus the remainder. Yes?
Should the first clause be RQ?
RQ?
Because if it's D, isn't it?
Oh, yeah, thank you. Yeah, I agree. So it's so this thing that I'm writing in red, it was previously a D, but of course that has to be a Q. Good. Other questions? All right. That looks kind of washed out to me. Let's see. Is that better? Or should I turn the light off? Nope, that's the backlight. Is that any better than it was before? Or was the other way better? It's about the same? All right. What did you say?
It's fine both ways.
It's fine both ways, okay. So, so that's, actually quite similar to like the Fibonacci functions. The only real distinction here is that now there's 2 outputs. But, that's kind of not that big of a difference. It's the f function that sort of is, that causes a disturbance. So now it's, again, divide 23 by 4, and this time it's going to be using this f. So f of n and d is defined as, in this case, let's consider. So if n is less than d, let me make sure I'm using the same symbols. So when n is less than d, so like if I handed you a pile of 2 M&Ms and I said make groups of size 4, then how many groups could you make? 0. So this would be, the answer would be 0 and n. And then unfortunately, it doesn't really matter too much, but observe that f and g, at least the way I wrote them on the homework, one of them G outputs what, Q and R? No, it outputs R and then Q, like that. but f is the other way around. I wish I hadn't done that, but fine. So what this is saying is that if that's true, then you can make no groups, and what's left over is n. And then otherwise, the answer would be q plus 1, comma r. So otherwise, and then we have this new thing that more or less we've never seen before in our class, where q and r is f evaluated at different arguments at n minus d. All right, so this is the first time where we've ever had something like that, that where. So none of the other functions have had that. And what I want to emphasize to you is how this process works. So now I'm going to have an aside. So the g function, the g tilde pair of functions will work like this. So now I want you to imagine we've got a sequence of children that are sitting in a row, just like y'all are sitting in a row. So suppose that I put a can, just like a bucket or a bowl or what have you, and I put 23 M&Ms in it. So 23 M&Ms are in it, and then in addition to that, I've got a counting device. Those clicker things where like they're usually made out of some nice metal. It's about as big as your fist, and you can click on it, and then every time you click on it, a counter increments by 1, and then you can turn a little knobby to make it go back to 0. Okay, so if you play baseball or something like anything like baseball, those are very often used, to count things like pitches and things like that. So imagine that we've got a bucket with M&Ms, and we've also got that counter. So the rule is we're going to set up all the kids side by side there, and say that we're playing a game with M&Ms, and if you do it correctly, then you'll get to eat the M&Ms. So then that's one of the fastest ways to turn children into scientists, because now this is serious business. So the rule is going to be that you're going to be handed the clicker, the counter, and the bucket. And if it's possible for you to take 4 M&Ms from the bucket, then take your 4 M&Ms and click the counter, and then pass the bucket and the clicker to the next child. So you pass it to the next one. If it comes to pass that there's not enough M&Ms for you to take 4 of them, then you stop and say, I have determined the answer. The remainder will be however many M&Ms are in the bucket, and the quotient will be whatever the counter says. Okay, everybody got the idea to make the physical analogy? All right, so it would be like this. So this is my artist representation of a child. Okay, that dot there. Now well, concerning G, if you look at the signature of G, G has 3 symbols, right? 1, 2, 3. R, D, and Q. So we have, to begin with, we have R is 23, D is 4, and Q is 0. So that's how the process begins. That means 23 M&Ms, we're making groups of size 4, and the counter currently reads 0. Okay, so then can you make a group? You can. So you do, and you also click. So now what remains in the can is 19 M&Ms. We're still making groups of size 4, but we click the counter, so the counter currently reads 1. All right. Can that child take a group? Yes. So then what remains is then 15. We're still making groups of size 4, and now the counter reads 2. Can that one take? Yes. So then now what remains in the can is 11 M&Ms. We're still making groups of size 4, and the counter reads 3. Can that one take a group? Yes. So then the group is taken. So now there's 7 in the can. We're still making groups of size 4, and the counter reads 4. Can we take a group? Yes. So now there's 3 M&Ms in the can. We're still making groups of size 4, and the counter reads 5. And now the behavior finally changes because what? Right, we can make no further groups because there's 3 M&Ms in the can. You can't make a group of size 4. So this child looked at the state of the computation and says, "Ha! I know now. I know that the remainder is 3 and the quotient is 5." Okay. Now here's a different way to do it. So this is the way G does it. So now with the same children and buckets and what have you analogy, I want to explain what F is doing. So F is going to achieve the same answer. It's going to achieve the same answer as the G functions, but it's going to do it without the clicker. Okay, so we don't have the click thingy. Rather, the way it's going to work is now we're going to have the following rules. We're going to say that okay, the can is handed to you, and you don't not the clicker because we don't have that. The can is handed to you, and you're to look at the can and ask if you can make a group or not. So if you are able to make a group, then take that group out of the can and tell the person next to you to tell you the quotient and the remainder. So you just tell them, you do it. Okay. When they get back to you, who knows how they're going to do it, but somehow they get back to you and they tell you the quotient. For example, let's say that they say that the quotient is 10 and the remainder is 2. Well, here's the deal. That's what they're telling you. But before you took your group, before you handed the problem to them, you took a group, right? And they told you that they were able to make 10 groups. So what's the actual number of groups? 11, right? Because they said they could make 10, but you took one. So actually the correct number of groups is actually one more than what they say. So again, if you take your group and then hand it to the next person, and they get back to you and say that I was able to make 2,369 groups, okay, and they hand it back to you, then how many groups are there actually? There's actually 2,370, right? Because you took a group before you gave it to them. You get the idea? So now the state of the computation, rather than that, looks like this. So what we have is that, to begin with, is that there are 23 M&Ms in the can, and we're supposed to make groups of size 4. So then we have no idea what the quotient and the remainder could be whatsoever. So rather, we're just going to look at this and say, well, can I take a group? And the answer is yes. So you take a group and hand the can to the next child, and now you tell them you do it. You compute the quotient and the remainder. All right. So now this one has 19 groups of size 4. Can this one make a group? Yes, of course. Now this one is working with 15 items in groups of size 4. Can that one make a group? Yes. So now this one has 11 items making groups of size 4. Can that one make a group? Yes. So this one has 7 items, and we're making groups of size 4. So notice that this child told that child, hey, tell me what the quotient and the remainder is. And then that child said to that child, okay, you tell me what the quotient and the remainder is. Okay, and this one said to that one, you tell me. And then that one said to that one, you tell me. So no one knows anything yet, right? No one knows anything. This continues to right here. So n is 3, and we're making groups of size 4. So here's what I want you to to understand, is that this child, if you handed the child, they're just following the rules. You handed them a bucket with 3 M&Ms in it and told them to make groups of size 4. Well, what, from their point of view, ignoring everyone else, what's the quotient in the remainder? How many groups can this child make? 0. And what remains? 3. So for the first time in this whole consideration, it is just now that someone can actually say something about what they believe the quotient in the remainder to be. So this child is under the impression that, the quotient is actually 0 and the remainder is 3. Okay? And then, they turn back and say, this one reports back and says, hey, I was able to figure out that there's actually, the quotient is 0 and the remainder is 3. And then this child says, okay, thank you. But remembers that before I asked that one to calculate the quotient of the remainder, I actually took one group. So what's from this child's point of view, what's the quotient in the remainder? 1 and 3, right? So this one says, it's actually 1 and 3. And now this one reports back to that one and says, hey, guess what? I figured out that the quotient is 1 and 3. But then this child remembers, actually, I took a group before I handed you the bucket. So from this child's point of view, what's the quotient in the remainder? 2 and 3. So can you see it's going to go all the way back? Oops. Interesting. So what I want you to see about this, again, just sort of analogizing this to a sequence of children following instructions about M&Ms and what have you. Notice that the computation for this one, in some sense, only proceeds to the right. That's it. But this one, in fact, computation proceeds in both directions. So first, going this way, subtractions are occurring. Subtractions until you hit the bottom, right? And then you have to proceed back, and then you're incrementing the counter. So in this one, I said you've got one of those clicker things, like click, 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 and you're handing the clicker and the bucket to the next kid, right? Blah 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 blah. This one, there's no clicker, but in some sense, a clicker still exists because what's happening is that the computation is going that way, and then all of these children are waiting for the person next to them to finish. So going backwards in the computation is like clicking the clicker. So to that end, we want to be able to sort of represent this computation nicely. So here's one nice way to illustrate the computation, with dots and arrows and things like this. Here's another way, and this second way is going to be more useful than the dots way. So I'll evaluate f of 23 and 4, and I'm going to do it using tables. All right, so what I want you to see is that in the definition of f, we have 4 symbols. 2 input symbols, N and D, and 2 output symbols, Q and R. So what I'm going to make is a table that has 4 columns in it, 1 for N, 1 for D, 1 for Q, and 1 for R. So to evaluate f of 23 and 4, I've got this table here. So this will be N, D, Q, and R. So of those 4 symbols, which, if any, do I know currently? N and D, right? I know that these are 23 and 4. But remember how this works is that you know, can you take your group, your handful? Yeah, you can, and then you ask the person next to you to do it. Well, immediately now from this position, what's going to happen is that this one is going to immediately need to ask, well, okay, then what is f of 19 and 4? Well, to evaluate f of 19 and 4, we'll need a table. All right. So we know that n is 19 and d is 4. And now, you know, can a group be made? Yes. So a group is made, and then you ask the next person to do it. So this one immediately is going to say, okay, I need someone else to evaluate f of 15 and 4. But, you know, to do that, we'll need a table. So we know n and d are 15 and 4 respectively. All right, so can a group be made? Yes, a group can be made. So, you know, we'll make that group and then say, hey, someone else. I need someone to evaluate f of 11 and 4. But to do that, we'll need a table. And we know that's 11 and 4. So now, can a group be made? Yes. So we you know, remove that group and then say, hey, we need someone else to evaluate f of 7 and 4. But to do that, we're going to need a table. And we know that n and d are 7 and 4 respectively. And then, you know, we ask, can we make a group? And the answer is yes. So we remove that group, and then we realize, I need someone to evaluate f of 3 and 4. And to do that, we're going to need a table. Just ran out of pencil. Okay, so we have a table. And currently n and d are 3 and 4 respectively. So I'd like for you to observe that you know, there's currently what, six tables in existence. So they all exist. And so far, no one has been able, no table. And if you analogize it to, you know, little kids sitting in a row, no one's been able to figure out anything about the quotient and remainder. Everybody's currently still, it's a complete mystery to everyone. So, you know, this one's finally able to make a conclusion, because there's 3 M&Ms and we're supposed to make groups of size 4. So from this, you know, table slash child, what have you, from this one's point of view, what is the quotient in the remainder? 0 and 3. So that means that the new state of the table is that, that taking rows to mean, the state at a certain time, this was 3 and 4, unknown and unknown, and now the state of the table is 3 and 4 and 0 and 3. Okay. So now this one is able to report back and say, hey, you know what, I did it. So this comes back to right here. And this one says, okay, well, so that means that my current state is now 7, 4, 0, and 3. But the thing is that before we asked that one to make a calculation, actually we took a group. So this, that one reported to me that the quotient was 0, but actually because I took a group, what's the real quotient? It's really 1. So the state becomes 7, 4, 1, and 3. And this one says, haha, I'm done now. And reports back. And reports back to this one. And so the state of this one becomes 11, 4, 1, and 3. And this one says, okay, thank you. But before I asked that one to calculate, I actually took a group. So what's the real quotient? It's actually 2, right? 1 more than what that one reported. Okay, so this will be 11 and 4 and 2 and 3. And this one says, I'm done. I can report back to the next child, to the child who asked me to do this in the first place. So now this is 15 and 4 and 2 and 3. And again, this one is able to say, well, yeah, has actually 1 more. So 15 and 4 and 3 and 3. And it just keeps going back up. So 19 and 4 and 3 and 3 becomes 19 and 4 and 4 and 3. Good. And then so this becomes 23 and 4 and 4 and 3. But I took a group before I asked you to do your work, so that means it's 24 and 4 and 5 and 3. And so as a result, we're able to say, therefore, f of 23 and 4 is 5 and 3. Meaning 5, the quotient is 5 and the remainder is 3. Interesting. So believe it or not, when you write, because you were asked to make a MATLAB version of this code, and when you do it, this is actually a fairly accurate representation of exactly what MATLAB is doing. Okay, every time you enter a function, like if you're at the console, the this thingy, the blah, and you type f of 23 and 4, then effectively what MATLAB does is it literally makes more or less a table of values with one column for each input variable and 1 column for each output variable. Okay, and then because f is a recursive function, this function is going to call itself. So when it does call itself, it makes another table, which in turn makes another table, another table, another table, another table, until it hits the bottom, and now they start reporting back to each other. We don't really need to get too much computer science-y in terminology, but the name of these things, these are called stack frames. That's what they're called. So more or less, in a recursive function like this, every time you recurse, there's a new stack frame. In the same kind of way that you can, imagine the children analogy. Imagine a magical situation where just no children exist, but just by the act of turning to the side and saying, hey, I need someone to continue the computation for me, some child poofs into existence, like poof. Now they exist. And it just continues until it reaches the end. And then when this one comes back, this one poof, disappears, gone. Okay, and that is effectively how the computation proceeds. Now, here's the deal, is that comparing these, you can see that stuff is happening going down. Specifically, we're subtracting, we're doing n minus d when we're going down. And then what are we doing when we're going up? We're adding, right? We're incrementing q. We're saying q plus 1. Okay, so like from there to there. So that's what happens when we're going up. So you can see this f is sort of going both ways, but this one's just going that way. So all the functions that we've done so far have been like this. With the exception of, that's not exactly true. That's not entirely true. But there was one that was like this, but it's sort of hard to see that that's happening, and it was the pyramid function. The pyramid function actually does this. The recursive one. The human Fibonacci one does this. And what I want you to see is that this act of doing stuff on the way back, that causes a lot of problems when you're trying to figure out, first, how to write something sensible on a page. So here's a sensible way to write it. And second, how to get MATLAB to do it. Okay, so each one of these going down, so like this, down, 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 that's a recursive call. So that's where the function is calling itself. Anything that needs to occur before you go down, before you make the recursive call, these things are called pre-actions. And then anything that you need to do after the recursive call returns, such things are called post-actions. Okay, so that means that in the MATLAB code, if this function really was, if it really was named f, that would mean that you're going to make a recursive call somewhere, and it's going to be like this. So it'll be like q and r is equal to f of I'll say a and b, say, like this. So that's where we are recursing. So if you look at the definition of f, this one, so f of n and d is going to need to end up calling that. So if I'm just comparing a to that one and b to that one, what's the formula for a? N minus d. And what's the formula for b? D. So what I'm saying is that these are things that you need to calculate before you recurse. Specifically, so that means in the file, in lines that precede the recursive call. So up here, these are the pre-actions. So we'd have to say that what's the formula for a? N minus d, right? And then I'll forget the semicolons. You'll have to deal with that. And then what's the formula for b? Just d, right? So we're saying, okay, this is getting prepared to call the next child into existence, or if you like, the next stack frame, or just the recursive call. So then now down here, when you're down here, that means that however it happened, that child got back to you and said, hey, I figured out that the quotient is q and the remainder is r. Well, fine, but what's the real quotient? Q plus 1. So down here, these are the post actions. Okay, so I'll just, I leave it to you to think about what should go there. Okay, so specifically the difficulty of this this f, both from the point of view of like computing with pencil and paper, and from the point of view of writing a MATLAB function. All of the MATLAB functions that we've done so far, there has either been only pre-actions or only post-actions. And as a result, all the functions all the recursive functions that you've done have been sort of simple. So you either there were none of these and only those, or vice versa. But this one that we're looking at has both. So that's the complication. Good. Any question about it? Any question about it? Okay, good. So now, well, what if I want to calculate something like, say, like divide 2,370 by 9. Okay, and suppose I'm going to do it with G, because G is a little easier to write down than the F one. That would mean that I'd say, all right, I'm going to do G of 2370 and 9, which is immediately going to call G tilde of 2370, 9, and 0. Okay, of course that 0 is a counter, saying how many groups have we been able to make? None so far, right? So can we make a group? Sure we can. So we'll recurse to 2, 3, 6, 1, 9, and 1. All right. Can we make a group? Sure we can. We'll recurse to 2, 3, 5, 2, and 9, and 2. And I suspect you can see that there's a ways to go, right? So there's a lot of steps here. ... We'll eventually get to G of 12. There'll be 12 left. We're still making groups of size 9, and we will have made 262 groups. That's a lot of groups. And then can we make another group? Yeah, one more. So then now we'll have G tilde of 3 and 9 and 263. Do you observe that we're no longer able to make any groups of size 9? As a result, the answer is 3 and 263. So what we're saying is therefore the remainder is 3, and the quotient is 263. And this would mean, among other things, that we should be able to write that 2370 is equal to, so the dividend is equal to the divisor multiplied by the quotient plus the remainder. So let's verify that's really true. So 9 multiply 263 plus remainder. There's the, can you see it? I can't really get it at a good angle. Well, whatever, 2370. All right, so now the answer to this question was that the quotient was 5. And how many children needed to come into existence? 6, right? And that's going to always be the case. If the quotient is 8, 9 of these happen. If the quotient is 1,000,000, 1,000,001 of these happen. So for this style of computation, if you take each arrow to mean a step, this one would take, the quotient was 5, so it'll take 1, 2, 3, 4, 5 steps, and like that. And this one will take that many, and then we have to go back, so double the amount. So how many steps would this take? More or less. About 263 steps, right? you know, maybe one more, you know, depending on exactly how you're counting. So this takes a lot of steps to do, doesn't it? Now let's venture back in time, and instead let's divide 2370 by 9, but instead of using G or F, let's do it the way Miss Harris told us to do it, you know, in 3rd grade. So you do it like this. You write 2370, and then I want to, wait a second, I want to space those numbers out a little bit. Two, 3, 7, 0. So 2370 is in the house, and 9 is outside the house, and 9 wants to come in. So you first look at the leftmost digit and ask, well, how many 9s can you take from 2? None, right? So then you write a 0 right there. And depending on your instructor, they might not have written a 0. They might have just written nothing. So then now you take another digit, and now you ask, all right, how many 9s can I take away from 23? 2 of them, right? So then you write the 2 right there, and that 2 jumps off the house, hits the 9 on the way down, and that's 18. You write that right there, and then you subtract. And you make the subtraction, and you get a 5. And it's good that we got a 5, because 5 is less than 9. If this number were 9 or greater, that would mean we had made an error, right? Because that would have meant you could have taken another 9. All right. So then now you carry this stuff down. And now I'll ask, you know, just to be sure, how many 9s can I take away from 5? 0, right? And it has to be that way, because otherwise we'd have made an error. All right, so then we'll take another digit, 50, and view that as a 57. How many 9s can you take from 57? 6 of them. So I write a 6 right here. That 6 jumps off the house, hits the 9 on the way down. That's 54. You write it under there and subtract, and get a 3. It's good that that's a 3, and it's less than 9, because if it were 9 or greater, that would mean we had made an error. That would have meant we could have taken at least one more group. So then now you carry down the 0. And fine. So then now, we can't take any 9s away from 3. Good. But can we take any 9s away from 30? Yeah? How many of them? 3 of them. So you write the 3 right here. The 3 jumps off the house, hits the 9 on the way down, multiplies to become a 27, and you subtract, and you write that right there. And the process is finished because, you know, we've run out of digits to carry down. Okay, so as a result of this computation, you know, we conclude that the quotient is that number, and the remainder is that number. Of course, that's the same answer as the g functions. But what I want you to see is that the g thingy, doing it like this, we had to perform one step, basically for every time we wanted to click the quotient, right? So this takes number of steps that's on the order of the size of the quotient, whereas this, you know, sort of viewing this as like a single step. Do you see that we basically took like counting that one, where we said, well, we can't take any 9s, so, you know, we'll count that as a step, and then to do that was a step, to do that one was a step, and to do that one was a step. So like this took 4 steps, and that's better than 263 steps. All right. Why did it take 4 steps? Why not 10 steps? In the end, it has to do with how many digits are in the number, right? Because that's how it goes, right? You say, well, let's consider the leftmost digit, and you do something. And then you consider the next digit, and you do something. And the next digit, you do something, and the next digit, and you do something. So like a billion has 10 digits in it, right? It's a 1 followed by 9 zeros. So if we were to, do like a billion divided by 9 with g, then that would take like 100 million steps. A lot. But if we were to do it in the grade school way, that Miss Harris taught us, a billion has 10 digits in it. How many steps would it take? About 10. And that's less than 100 million, right? So can you see that, oh, Miss Harris, she was on to something. she had some good idea. All right, so let's try and formalize what Miss Harris was talking about. Okay, so we want to divide 2370 by 9. But now we need to make all the things that we're doing so explicit that you could write a program that does it for you, because you're going to. Okay, but it's hard to say to MATLAB, look at the leftmost digit. What does that mean? Okay, so what we're going to do is the first thing we're going to consider sequential powers of 10. Powers of 10. So the first one we're going to consider is 10 to exponent 0. Now what's that? 1. So we're going to consider 1, and then we'll consider the next one is 10, and then 100, and then 1,000, and then 10,000. Okay, and because the group size is 9, what we're going to be considering is that is it possible to take one 9 from 2370? So can you take away a single 9? And the answer is yeah. There's enough to take away a 9. And then the next question is that, well, then is there enough to take away 90? Yeah. Is there enough to take away 900? Which is to say 100 groups of size 9? Is there enough in 2370 to take away 900? Yeah. Is there enough to take away 9,000? Nah, there's not enough, right? There are not enough M&Ms in the bucket to do that. So that means that we're able to do that, we're able to do that, we're able to do that, but we're not able to do that. Okay, so what I want you to see is that that's the ones place, the tens place, and the hundreds place, and the thousands place. And if you look at the computation, do you observe that the first thing that we considered is we said let's look at the leftmost digit, and then we wrote a 0 there. That's saying that oh, we weren't able to take away any thousands. Okay, so the thousands place is 0. That's what that means. Okay. So now that we've established that we're able to take away groups of size 900, now the question is how many 900s? How many of them? So we've already established that we can take at least one. So the question is going to be, can we take 1, 2, 3, 4, 5, 6, 7, 8, or 9 900s? I don't need to write 0 because we already established we can take at least one 900, right? And I don't need to go on to 10. Why not? Yeah, because that'd be 9,000. And we already established that we can't take 9,000. All right. So then how many 900s? Okay, can we take, from 2370, can we take 900? Yes. Can we take 1800? Yes. Can we take 2700? No. Okay, so we can do this, but we can't do that. All right. That means that we can take 2 900s. That means that we have a winner. So that's the first digit. So now we're saying therefore the quotient is at least 2 multiplied by 100. Because we were able to take 100 groups of size 9 twice. So the quotient is at least 200. Yes?
Can you also exclude the 1 from the second step?
Well, I mean, in some sense, yes. Yeah.
But would it be harder to do it?
Well, I'm doing something, it'll be more clear why I'm doing it exactly this way in a moment. But in some sense, yes, we don't really even have to ask that because we already verified that. But we're not going to do it exactly this way anyhow. So the quotient is at least 2 times 100. So now we're going to, and we were able to take 1800, so we're going to take now. So the new dividend is well, we had 2370, and we just said that we're going to take 1800. So that's 570. So now this is the number that we're looking at. Okay. So we were just taking away 900s. Now what size are we taking? Now we're going to take 90s. All right. So can we take 1, 2, 3, 4, 5, 6, 7, 8, or 9 such 90s? All right. So then are we able to take 90 from 570? Oh. So we can take 90. So can we take 180? Yeah? How about, can we take 270? Yeah? Can we take, what's next? 360? Yes? Can we take 450? Yes? Can we take 540? Yes? Can we take 630? No. So we were able to do this, and this, and this, and this, and this, and this, but not this. So what that's saying is we were able to take away 6 90s. So as a result, that's the one of the winners. Haha, 6. So now we're able to conclude that the quotient is at least, well, we had already established that it was at least 2 times 100. And now we just took away 6 in the of size 10. So this would be plus 6 multiplied by 10 there. Okay, and now we can say, okay, the new dividend is, well, we just had 570, and we just took away 540. So the new dividend is 30, and that's, you know, where our eyes are. So first we said, how many 900s can we take? And we answered that question. Then we said, how many 90s can we take? And we answered that question. So now what's the question? How many 9s can we take? Nines, like that. How many 9s? So we can either take, you know, we have to figure it out. Can we take 1 9, 2 9s, 3 9s, 4 9s, 5 9s, 6 9s, 7 9s, 8 9s, or 9 9s? Again, we don't have to write 0 because we, you know, we already know that, well, I guess, in fact, we could write 0. But at any rate, we have this many symbols. So how many 9s can we take? So can we take a single 9? Yeah. How about 2? Yes. How about 3? How about, what's next? 36? So we can take this many, this many, this many, but not this many. So what does that tell us? Right. So that's that digit. And we can say, therefore the quotient, we don't have to say at least anymore. We don't have to say at least because this was the last step. So now, in fact, it's just the quotient is exactly 2 at size 100, 6 at size 10, and 3 at size 1, which of course is 263. And then the remainder is 30 less 27, which is 3. So I suppose that you know, there is sort of an implicit 0 here, because in principle it could have come to pass that we couldn't take any. Right? So I guess there's a 0 here. Okay. So I have a question. There's this many choices for how many of this kind you can take. So there's 10 choices there, right? So there's 10 choices. What if we were operating in base 8? How many choices would there be? 8, right? And if we were operating in base 20, there'd be 20 choices. So if we're operating in base 2, how many choices? 2. Now it's going to turn out that in base 2, these two operations, meaning to say figure out the scale. Should we take away, you know, that many, that many, that many, that many, that many, and this one together, they're going to sort of collapse into a single choice because there's just 2. Again, the joke is that you know, 2 is not an odd prime. Is the oddest prime. So when we make the base 2, the calculation is going to be even easier, in fact. So can you see that this is what this is like a really overbearing way to write down the division thingy that you learned in Miss Harris's class. Okay, you've got to figure out the scale. This is the way you can, you know, convince a machine. I want you to look at the leftmost digit. Right? That's what this is saying. And then, you know, all right, how many can you take away? So now let's do it in base 2. Any questions so far? All right, so in base 2, divide 2370 by 9. But now we're going to do it in base 2. All right? So the first step is instead of considering sequential powers of 10, we're going to consider sequential powers of 2, and we're going to take that many. So here's the first several sequential powers of 2. So 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. Okay, so now what we're asking is that because we're dividing by 9, we're asking, can we take away this many 9s, or that many 9s, or that many 9s, or that many 9s, etc. So we're asking, can we take away 9? Yeah. Can we take away 18? Yeah. How about, oh man. 18, 36, 72, 144. So again, this is going to go up until we get something that's more than 2370. So can we take away 288? Yes. Can we take away 576? Yes. Can we take away 1152? Yes. Can we take away 2304? Yes. Can we take away 4608? No, right? So you can see, we finally went too far. Okay, so then could we do this? Yes, 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 no. Okay, So that's saying that because we're dividing by 9, this is saying we were able to take 256 nines. That's how many of them we were able to take. All right. So now we can say, therefore, the quotient is at least 256, and the remainder, well, not remainder, I suppose. I guess it's the dividend currently. So the new dividend is, well, we had 2370, and what we did is we said, well, we took away 256 nines, and that's that much. So 2304, like that. And what's that? 66? Is that right? Yeah, 66. Okay. And now, in some sense, the question is quite simple, because we said, can we take 256 nines? Okay, and that is to say, can we take away that much? And the answer is yes. So can we take away that much? No. So that means that we couldn't do 128 nines. Can we take away 64 nines? No. How about 32 nines? How about 16 nines? How about 8 nines? How about 4 nines? Okay, so now the answer is yes. So why can we take away that many? Yeah, because it's 66, right? What we're doing is we're traversing backwards in the list until we get a number that's less than 66. So again, we just did this. So we said, how about that? Nope. How about that? Nope. How about that? Nope. How about that? Nope. That one? Nope. That one? Yes. Yes, because if we take away 4 nines, that's 36. So we can do that. Okay. So, this is the first winner. So, in some sense. So, yes. And then this is a winner. So we can say, therefore, the quotient is at least, well, we said it was at least 256, and then we just took 4 more. So it's at least 256 plus 4. And doing that, the new dividend is, well, we had 66, and we said that we're going to take away 4 nines, which is 36. So that means that the new dividend is 30. And so now we're going to traverse backwards in the list until we can find something less than 30. So, we can't take 36. Good, because we did that. But can we take that? Can we take away 2 nines? Yeah. So therefore, the quotient is at least 256, because we took away 256 nines, and then we took away 4 nines, and now we're saying we're going to take away 2 nines. So that's a winner. And so the new quotient, new dividend is 30, and then we just took away 18, so fine. And then so that'd be what, 12? So the new dividend is 12. And now we go backwards and say, can we take away 1 9? Yeah. So, and because that's the lowest power of 2, that means that that's where the answer is definite. So we don't have to say at least anymore. In fact, the quotient is 256 plus 4 plus 2 plus 1, which if you add that up carefully, that's 263. And the remainder, not the new dividend, but rather the remainder, because this is the end, will be 12. And then we just took away 1 9, is 3. Hey, So then sort of viewing it like this, you can sort of count, like each one of these has a step. right? So we only ended up circling 4 numbers, those 4. But the number of steps, we could say we had to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we had to go backwards. So say 20. So we did this in 20 steps. Now, is that better than 263? Yeah, it is. Let's think of a really, really big number. So an example of a big number is that, like the number of protons in the observable universe. That's a lot. That's about 10 to exponent 80. So that means like a 1 with 80 zeros behind it. Now, if you were to do the base 10 algorithm that you learned in Miss Harris's class, if you were to do this, if you were to do 10 to exponent 80 divided by 9, about how many steps would it take? 80, because it's got about 80 digits. That's how long it would take. It would take 80 steps. But if you were to do it with G, about how many steps would it take? It would take about 10 to exponent 79 steps, which is a lot. You could do it from now until like the universe runs out of all energy whatsoever. You would never finish if you were doing it by hand. Not ever. So the difference between 80 steps and so many steps that the universe would undergo its heat death before you finish. That's a big difference, right? And so the number of steps that this procedure takes is proportional to the number of digits in whatever base that you're in. So if you're in base 2, there's slightly more digits than the number of digits in base 10. But the thing is in base 2, you don't have to figure out, do I take 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9. You don't have to figure that out because you're either going to take 0 or 1. So you sort of make it up, make up the difference there. So any questions about this? In fact, this is a fairly accurate representation of how the computer actually does division. And this is going to be our next task, because you're going to write Euclidean division, but it's going to do it this way. And I hope that looking at this, this kind of procedure, that you're getting a kind of a strong echo from the guess the natural game, right? Because you're sort of like increasing the scale bigger, 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 until you say, this is right, and then multiplying by 2, and then once you've found the boundaries, then you start decreasing things by a factor of 2 because you're computing a midpoint. Okay, very good. Have a nice Thursday.